Welcome. My name is Edmund Cape. I've been a data scientist in one form or another for several years, whether during my time as a PhD candidate and postdoc in academia, or during my time as a management consultant, or even as a sales and marketing operations analyst. I was continually amazed by how much time it took to conduct an analysis. I greatly appreciate you taking the time to listen to what I believe is a big problem in our industry. At the end of the presentation, there will be a link to Lucivia's data structuring and analytics software platform. This is something I believe is a solid solution to the problem. Without further ado, the problem we aim to solve. Data, analytics, decisions. Without analytics, it's just data. As a data scientist, this is a familiar mantra, where analytics is the golden egg, the linchpin, if you will, that informs business decisions. But not so fast. Before we can perform a meaningful analysis, we have to work with the data. So let's talk more about the data. In my experience, data structuring consumes 80 to 90% of my time. Having worked with many analysts and built teams of analysts, I know this experience is shared by many. Think back to the last analysis you were conducting or were relying on to make a decision or recommendation. How much time were you spending with the statistics versus structuring the data, scrubbing the data? Why is that? What is it about the data that takes so much time? I've put together a series of visuals that I think start to tell a story. Data is opaque. When we're dealing with millions of records, gigabytes of data, it's not like we can open up an Excel sheet to review and adjust here and there. Data is prolific. It's amazing how much is out there. And of course, as analysts, the more the better to help explain the variance in the dependent variable, that metric that means so much to the business. The data might represent related information that comes to us in different formats. Some are gigabytes large with hundreds of fields. Others might describe a small but important subset of our subject universe. There's data that broadens the description of our subjects, new qualities or traits. Others might represent observations over time that introduce new subjects to our data universe. Not all data can be guaranteed unique. Overlapping data can be redundant and thus introduce multiple sources of truth. All of these possibilities exist not just at a table or file level, but at a field level. It's here that we combine the data one way or another, depending on the reliability of each source, never losing sight of the fact that we operate in a context where missing data is always a possibility. All in all, as the data comes our way, including that data with the latest information we've been waiting on for weeks, we have to put it all together and get it right fast. With all of these possible combinations, isn't getting it mostly right good enough? In my experience, those types of decisions, while immediately helpful, and let's face it, often required to get the job done on time, can introduce more work later, work that could have been avoided. As they say, there's no such thing as a free lunch. Okay, maybe not helpful, but there is a problem with getting it only mostly right. First, what is mostly right anyway when the statistical findings didn't land as I had expected? It's then that I start to wonder, was there something else I could have done while structuring the data? How much effort might it take to go back? Could I have included another control factor? Other things that come to mind: how often can I use the 80-20 prioritization rule before what I've done might be wrong? While prioritizing and streamlining will always be important, I still have to think about where it is likely critical to just do it the right way, despite the extra time it might take. It isn't rocket science. It's just going to take more time. These decisions that consider the trade-offs are ones I wish I just didn't have to make. And I suspect if I had the right tools, I wouldn't have to. But here, I digress. There's an expression, death by 1,000 cuts. In this next slide, we'll conduct a rough combinatorial analysis to to illustrate how large the solution set, the possible ways for the data to come together, can get. We'll use 3 files, each with 10 fields. Let's go step by step. First, gap filling, the code that involves case whenif or coalesce to catch and interpret the null values. A possibility for each field, so 30. Next, in the event we might have duplicate values, potential double counts, we have to dedupe accordingly. The code snippets involve selecting the distinct values for a field or a subset of fields, perhaps involving subsequent joins of data with a different number of records. You know the pain that can come with that. We have that consideration, say 30 times, once for each field. Of course, there are more than that, but we'll keep it simple for now. In the event we have related information from multiple sources, we have to perform a union of that information. Union expressions require we match names, again, up to 30 possibilities. When there's overlap, the choices for determining the source of truth, for the first choice, we have 3 options, for the second, 2, and for the last, 1. So that's 6 possibilities for the 10 fields that we combine a maximum of twice. So that gives us a total of 120 possibilities. Next, the joins that add more fields to each of our subjects. There are 2 possible joins of a maximum 30 fields, so 32. Next, gap filling, where the subjects in each join didn't necessarily align. Depending on the number of fields that are being joined, the way I'm thinking about it anyway, it's a count from the cumulative number of fields after each join. So for instance, after combining the first 2 sources, say we have a table of 20 fields, that we then combine with the third source. So that would be 10 plus 10 for the first join and 20 plus 10 for the second join, for a total of 50. Or thinking about it differently, the average of 20 and 30, which is 25, times 2. This gives us a grand total of 292 possibilities. So not 1,000 cuts, but give me a couple more data sources and I'll get you there. The point is meant to be illustrative of how quickly the solution space can expand just with these 3 files, each with only 10 fields. The fact is that one way or another, we process and consider these possibilities to ensure that our data structure is correct. I provided a brief description of the code snippets involved for each step in the previous slide. Let's take a deeper dive into the code required to simply import the data into our database. The point I'd like to make here is how quickly these scripts become brittle, are difficult to manage, and ultimately fail to represent a complete description of our methodology. On the left, I have a SQL script that was seeded using an import wizard before being updated manually. There are many pain points here. Let's go through them one by one. First, there are 4 manual touch points for each field. There's the field name, the field type, and in some cases the field length, and of course, whether or not to accept null values. Decisions. Furthermore, there is no support for naming or renaming fields. So if I change a field name in one place, I have to manually find where else the code depends on that old name. One typo, and the script will break. Non-trivial, time-consuming stuff. Next, the code is an incomplete record of events. First of all, I don't know where the source of the information came from. The table name does not point to the external data source. Secondly, in the event I want to rename the fields, I don't have a record of how to map the old name with the new name. Next, processing null values is fragile. If I choose to be strict, all it takes is for one record to have the import fail. On the other hand, if I accept null values, I have to inject null value logic into my code that relies on the data to avoid corrupting the counts and joins. There is no way to enforce conventions across tables. Naming of related fields, primary key specifications, and this, in my experience, this last one's can happen quite a bit. A primary key might be treated as a string in one table and as an integer in another. If all of our records have leading zeros, we'll catch the error pretty quickly. But if only a handful of subjects have a leading zero in their ID, we might not catch the error until later in the process when trying to problem solve inconsistencies in our counts. Finally, any business logic that might need to be applied must be replicated for every source with related information. There's no support for that. Finally, it's here that I have to make productivity trade-offs. High quality involves trial and error to find the best approach, but doing so makes it more difficult to stitch together the various steps because I'm increasing the number of manual steps, which of course is also more difficult to review and audit. The precise place where I'm more likely to make a mistake is exactly where it's more difficult to review. Wouldn't it be easier not to have to make these trade-offs in the first place? Certainly not as often as we do now anyway. Before talking about the solution, let's recap. In order to perform an analysis, we need to structure the data. We know that data structuring can take a lot of time. Why? Well, data can combine in many different ways. Not all of them are the right way. It takes time to identify and consider how to do so. Why? The process is loaded with manual interventions, which requires painstaking care to manage using a brittle technology, which requires hedging our efforts, not knowing ahead of time exactly which effort will pay off in our analysis downstream. We have to make a lot of decisions along the way. And as you all may well know, the more decisions we have to make, the worse we are at making them. It's just how the brain works. The solution is an analytics platform with a completely reimagined process, a process built for analysts from the ground up, something attuned to ETL for analytics to reduce the time and cognitive load required to get it right. Design objectives. The process must dramatically reduce the labor required to complete an analysis. It must produce a perfectly consistent data set. Emphasis on consistent. I need to be confident that I did not introduce any bias by way of my methodology. Given the size of the solution space, I want a system that flags inconsistencies along the way and avoids crying wolf. A process that makes it easy to get it right. In parts assembly, they use non-symmetrical parts to make sure the pieces fit together in only one way, the right way. Similarly, in software, utilize a model that allows data to combine in only the ways that make sense. It provides validations along the way, and it needs to enable more engagement with colleagues and stakeholders. The more I'm able to engage with my thought partners, the less likely I am to miss something. Finally, a process that, once complete, performs a fully automated analysis, end-to-end, that makes it easy to iterate and collaborate. The inspiration for this reimagined process in part came from thinking about how data is different from the information it encodes. For instance, the infamous null value. That's data. But the information it encodes can mean different things that are critical to understand for the purposes of our analysis. In one context, it might mean 0. In another, it might mean something that didn't happen. In yet another, it might actually mean missing information. Another example is thinking about what information arises from the combination of fields versus individual fields and the sources per se. In particular, how each field work in combination to inform our statistical analysis, to describe the subjects for which we are observing. In the end, I believe we have a process that applies your domain expertise consistently throughout the universe implied by the data, a process that is organized around the information encoded both explicitly and implied in each collection of fields describing a subject or measurement. And given the ever-increasing size of the potential solution space, a process that identifies redundancies in both the workflow and the data, and thus opportunities to reduce the size and complexity of the task. A process that ensures the analysis is using a structurally complete and flawless data set. All in all, a tool that reduces the number of trade-offs I might otherwise need to make, if only because it just does the right thing automatically for me. Finally, one last analogy, if I may. A benefit of a modern self-driving vehicle is not so much that you don't have to pay attention, but rather driving such a vehicle enables you to pay more attention, but to fewer things. The result is a safer, more enjoyable drive where you feel more rested by the end of the trip than you would have otherwise. That's how I see Lucivia's data structuring and analytics platform. But unlike the self-driving vehicle, it gets you there a whole lot faster. See if you agree. Watch the software in action with our online demonstration. It's there anytime you're ready. Reach out to us anytime to see how to get Lucivia's analytic platform working for you today. Thank you.